TensorFlow is a free and open source library that makes implementing various machine learning algorithms much easier. There are lots of tutorials out there on how to get started with it, but I wanted to show a niche application for it, running it on a microcontroller. TensorFlow Lite is a subset of the TensorFlow repository intended to run on embedded devices, and there's a small piece of that subset that's meant for microcontrollers. Since microcontrollers are usually very limited in resources, you generally don't want to train a machine learning model on them. So a basic workflow is to train a model using full TensorFlow on your computer or some other server. You'll then convert that model into a TensorFlow Lite flat buffer file. This .tflite file works with regular TensorFlow Lite, but you'll need to convert it to an array in your language of choice for microcontrollers. For us, we'll create a C array and then transfer that over to our microcontroller so it gets loaded into memory. With the TensorFlow Lite for Microcontrollers library, we can now perform inference using our model on our microcontroller. Inference is the process of taking new data that has not been seen by the model before and feeding it to the model. The model then infers some information about that data. For example, if we feed it a photo, a model trained to look for cats would tell us whether it thinks there's a cat in the photo or not. I'm not going to get into training a neural network in this episode, as that takes a lot of time, and there are plenty of other great videos out there that show how to do that. For this episode, I'm going to start with a pre-trained model that I created in a previous episode. Please check out the Intro to TinyML Episode 1 video, which I'll make sure is linked in the description. In it, I show you how to use TensorFlow and Keras in Google Colab to create a 3-layer neural network that predicts the output of the sine function. It's a terrible way to create a sine wave in a microcontroller, but it's a great demonstration of how to train a very simple neural network for our purposes. All credit goes to Pete Warden and the TensorFlow team for putting this example together. Once we've trained the model, we want to test it by feeding it a few numbers. I'll specifically be looking at an input of 2. If the model runs correctly in our microcontroller, we should see an output of 0.9059. This should be close to sine of 2, which is about 0.9093. From there, we save the Keras model as a .h5 file, although it won't be very useful for us. We need to convert it to a TensorFlow Lite file first by calling the tfliteconverter.fromKerasModel function. Note that we optimized the model for size, but we're still doing everything with floating point values. There is a way to quantize the model's inputs, outputs, weights, and bias terms to 8 bits to save even more space, but I'm not going to get into that here. Finally, I wrote a quick function to convert the tflite file into a C byte array, which I'll save in a .h file. If you look at the File Explorer pane in Colab, you should see the model files that we created. I recommend downloading them all. You can use a program like Netron to examine the Keras and tflite model files. This can help you understand the input and output formats as well as how the layers are connected. Our generated .h file should have the tflite model converted into a C array, which I'll give it the global variable name of sine model. We just need to include this header file in our microcontroller code to import the model. Now that we have our model, we need to prepare TensorFlow Lite as a library. What I found is that TensorFlow really doesn't want you to use it like a library. They want you to modify automatically generated source files and then compile everything within their file structure. While this might work for some instances, I honestly find it very hard to use when you already have an embedded build system set up. For this example, I'm going to show you how to import TensorFlow Lite into STM32Cube IDE, and that's only because I'm most familiar with STM32 stuff right now. I'm using an STM32L432KC Nucleo board for this, as it's small but running an ARM Cortex-M4 processor. The steps I'm about to show you should work for any build system, including make. You'll need to run a make file inside of TensorFlow, which will generate a template file structure. You then copy those files over to your project and include the necessary header and source files in your build system. To generate the TensorFlow Lite file structure, you need to use Linux or macOS. I have not gotten this part to work on Windows yet. If you're on Windows, feel free to dual boot or use a live USB distro of Linux. I'm just going to SSH into my Raspberry Pi since I always seem to have one lying around. You'll need to have make, Python 3, pip3, git, and zip installed. Use whatever package manager you want to install them if you don't. From there, use git to clone the entire TensorFlow repository. I'll use a depth of 1, which means I only grab the last revision, saving some download time. Next, I'll go into the base TensorFlow directory and run the make command from there. I'll point it to the make file located in the TensorFlow Lite micro tools make directory and give it the portable optimized tag. I don't know if it's necessary for this demo, but this tag seems to generate a different implementation of a couple of source files optimized for microcontrollers, so I'll leave it in. We give make the generate non-kernel projects target, which leaves out a few template projects that we don't need. In this instance, make doesn't build or compile anything. It simply generates a bunch of template project directories for us to use, which can take a few minutes. While make is running, let's create our microcontroller project. I'll be using STM32Cube IDE, but as I mentioned, you can use almost anything. Just note that the steps for including source files and linking object files might be different for your development environment, but the process is essentially the same. I'm going to start a new project for my Nucleo L432KC board. Note that we must use C++ as the target language here, which means choosing to use a C++ compiler, as most of TensorFlow is written in C++. I'm going to enable one of my timers to continually tick every microsecond, which we can use to measure how fast inference is running for our model. Since I want this to run as quickly as possible on my microcontroller, I'm going to use the high-speed internal oscillator and kick up the main clock to its maximum of 80 MHz. Let's save to have CubeMX generate code. In this IDE, I need to rename main.c to main.cpp so that the build system treats it as a C++ file. At this point, the make process on Linux should be done. To start, I'm going to copy the sign model header file into my project directory. Then I'll navigate into the file system of my Raspberry Pi, which I've mapped to my Windows machine using SSHFS. Navigate into the TensorFlow repository, then into TensorFlow Lite, Micro, Tools, Make, Gen, and Linux something. This folder's name will likely change depending on your specific computer and operating system in which you called make. In PRJ, you should see a whole set of project templates. I recommend ignoring the test ones for now, but you can look at any of these to get an idea of how you should structure TensorFlow projects. Note that TensorFlow wants you to change the main program in one of these templates to get your project to work, but we're not going to do that. Go into Hello World and you should see a number of build systems that the Hello World template was generated for. Once again, we're going to ignore this as I want to use TensorFlow Lite as a library in my build system of choice. Make should be neutral enough, so let's go into that directory and copy the TensorFlow and third-party directories. These will act as our TensorFlow Lite library. Navigate back to your microcontroller project directory and create a folder named TensorFlow_Lite. Paste the TensorFlow and third-party directories in there. The third-party folder contains some open-source tools needed by TensorFlow that should have been automatically downloaded when you ran make. In the TensorFlow folder, go into Lite, Micro, Examples, and Hello World. This folder holds the main application that we're supposed to modify. Feel free to look in the main and main functions files to see how they want you to make a TensorFlow Lite for microcontrollers application. While you could use this template and make it work with your specific microcontroller, we're not going to do that. So delete the examples folder and everything in it. Back in our IDE, we want to refresh the Project Explorer so that it sees our newly added files. This includes the TensorFlow Lite folder we added as well as the model file. Now, we need to tell the build system to include these header and source files. If you're working in Eclipse or one of its derivatives, go into Project Properties. In C, C++ General, go to Paths and Symbols and open the Includes tab. Click Add and select the TensorFlow Lite folder from your workspace. You'll want to add it to all languages and configurations. Repeat the process for the third-party flat buffer include, gemlo-p, and rui folders. Because of how the includes are structured in the TensorFlow source code, you must add these third-party directories just like this. Check to make sure that the included directories show up in the C and C++ languages as well as in the release configuration. Go to the Source Location tab and add the TensorFlow Lite directory to both debug and release configurations. Click Apply and click Yes if asked if you want to rebuild the index. Note that if you're working in Make, you'll want to ensure that your header and source search paths include these directories. There's one file that we need to edit in the TensorFlow library that will allow us to print out debug information. Go into TensorFlow Lite, TensorFlow, Lite, Micro, and open debug_log.cc. Comment out the include C standard input-output line as well as the debug log function. On a separate line, rewrite the debug log function but include the attribute weak symbol and leave the function body blank. By using the weak symbol, we can override this function in our main program. We need to keep extern C as this is a C function which will be called inside of a C++ program. Back in main, implement the debug log function however you see fit. I'm going to simply print out the string argument over my UART connection, which is connected to a USB to serial converter on my Nucleo board. Since the function does not provide me with an array length, I'm going to use the string length function to figure that out and pray that the string is null terminated. We'll need to include the C string library for that to work. I'm going to give only a broad overview of this code for the sake of time, but I'll add a link to it in the description so you can dig into it if you wish. First, we need to add our includes. These point to just the TensorFlow Lite functions that we'll need in our program. Notice that I also include the model file that we created at the beginning of this video. Next, we want to define some global variables. We'll put them in an anonymous namespace so they're only accessible in this file. These are pointers to our error reporter, model, and input and output buffers. The important thing to note here is the tensor arena size. You'll have to play a bit of a guessing game here. I'll start with 2 kilobytes of space for the arena, which is just a chunk of memory that TensorFlow Lite needs to perform its calculations. If your allocate tensor arena function fails later, you'll likely need to increase this size. In main, I'll add a few variables that our program needs, such as a buffer for printing out strings over UART, return status codes, and a timestamp in microseconds. Just before the super loop, we'll add some initialization code. First, we start our timer so that we can measure how long inference takes. Next, we create an error reporter, which is needed by the inference engine to help us troubleshoot problems. I'll write a message out over the error reporter to make sure it shows up in our serial terminal. Next, we read in our model array. Note that the variable name here should match the name of the array in the sign model header file. We also check to make sure that the TensorFlow Lite operations schema version in the model matches the version of the TensorFlow Lite schema we're using here. Then, we want to create an operation resolver, where we only include the specific operations required by our model. If you want to see the TensorFlow Lite operations that are supported, check out the microops.h file. Since our model only uses fully connected or dense layers, we just need to register the fully connected operator with the op resolver. We create an interpreter object and pass in pointers to our model, op resolver, arena buffer, and error reporter. We then call the allocate tensors function, which configures the arena buffer we created. If this fails in your code, it likely means that you didn't create a large enough arena, so you'll need to go back and adjust the tensor arena size variable. Finally, we assign a couple of pointers to our input and output buffers to make accessing them easier. At this point, we're ready to start making inferences, but I like to check the dimensions of the input tensor first. So we'll print out the number of elements in the input tensor buffer just to be sure, which in this case should be equal to 1 element, a floating point number. In the while loop, I'll put the floating point number 2.0 into the input tensor buffer. Note that I'm using a for loop here to demonstrate how you might fill up the input buffer with more than 1 element, but for this particular model, there should only be 1 element. We'll grab the current microseconds and then we call the invoke function to run inference. This is a blocking function, so your processor might hang for a while at this point. When it's done, I'm going to get the only element in the output tensor buffer. Once again, with other neural networks, this output buffer might have more than 1 element. Then I'll construct a string showing the output of the neural network and how much time has elapsed since our original timestamp. I'll print this string out over the UART port. In some build systems, like mine here, you might need to add a special linker flag to print floating point values with %f. So I'll go into Project, Properties, C++ Build, Settings, Tool Settings tab, MCU G++ linker, Miscellaneous. In other flags, I'll add the -u printf float flag for both debug and release configurations. Finally, I'll add a delay of 500 milliseconds before repeating inference again. When you build the project, you might get some warnings. I recommend reading them to see if there's something you need to fix. In my case, this warning looks to be something inside the TensorFlow Lite library that I probably won't use, so I'll leave it for now. With everything built, we can upload the program. In STM32Cube IDE, I do that by clicking Run and Debug. I'll accept the default debug configuration settings and open the debug perspective. I run my program and connect a serial terminal to my Nucleo board. If everything works, I should get some data showing that the output of the neural network is 0.9059, which matches the original test from the beginning of this episode. Also, we can see that it takes about 368 microseconds to run inference with this simple 3-layer neural network on our 80 MHz microcontroller. This is great! Everything seems to be working. There's just one last thing I want to try, as 368 microseconds seems to be a little bit too long. Let's stop our running program. I'm going to go into Project and set our active build configuration to Release. I'll rebuild the project. While that's going on, if you look in the tool options for debug configuration, you can see that there's a debug flag being set, which is not present in the release configuration. My understanding is that some of the code in the TensorFlow Lite files changes depending on this flag, which can speed things up if we remove it. It does mean that we'll be giving up some helpful debugging information though. Let's create a new run configuration and set the newly built release elf file as our application. This is what will get uploaded to the microcontroller. We'll set the build configuration to release in case we need to build the project again. When we click run, it looks like any new code will be built. This is an interesting point to stop and look at the output of the GNU size tool. From my understanding, add the text and data fields together to get the flash usage, which is about 50,000 bytes. You then add data and BSS together to get the predicted RAM usage, which is about 4,700 bytes in this case. When it's done, the program will be uploaded to the STM32, but it won't load the debugging perspective. Bring up the serial terminal and you should see that the program is already running. Without that debug flag, it looks like the neural network runs over 3 times faster. It's now taking only about 104 microseconds to run inference. This seems to be pretty quick to run a neural network, but the real question is, can we do anything useful with such a small neural network? That will have to be a discussion for another time. With that, please subscribe if you'd like to see more videos like this one, and happy hacking!